Good morning, everyone. Welcome to another episode of Kasal Talk Show. Today we are going to do Mathematica demonstration. I'm going to show Mathematica typesetting, mathematical typesetting, Wolfram language, compared to TeX or LaTeX, for example. And I'm going to demonstrate Mathematica notebook and typesetting in Wolfram language, and also the outline feature in comparison to Emacs org mod. So today is 2021, May 6th. Welcome, guys. Okay, I'm going to begin. Okay, Mathematica typesetting. So I'm going to show you an article. Search for TeX pestilence. Okay, this is my article, the TeX pestilence, why TeX and LaTeX sucks. That's Donald Knuth's technology for typesetting. So you can see this article written in 2004, 16 years ago. Here we have typesetting, and here is the code you type in LaTeX to show this mathematical typesetting, and I'm going to show you how you do that in Wolfram language. Okay, so on the left window, for those of you Emacs users, on the left window you can see all my Emacs commands and the keystrokes. For example, move cursor right, backward by word, or move by character, move down, move up. Any command, any key I type in Emacs, it will show the corresponding command on the pink window and the corresponding key. I'm using Kasal keys, and I'm using Wolfram keyboard. So Wolfram keyboard, let me show you my keyboard. Okay, so keyboard is, so that is the one I'm using. Let me show you. Okay, so you can see my keyboard. So this is Kinesis Advantage 2, and that is Ultimate Hacking. So you can see reviews I have, and video reviews of both of these keyboard. Okay, so now let's go back to Mathematica. And let's talk about the fantastic features of typesetting in Mathematica. Okay. I need to get a camera holder. Okay, so let's do. Okay, so let's see. So let's see Mathematica. So Wolfram language. Okay, so first thing I'm going to show you how do you type those things in Mathematica. Okay, so sum. Okay, sum. And by the way, I did about 5 or 6 videos on Mathematica. So if you are interested in Wolfram language, which is a fantastic programming language, in my point of view, it's the best programming language by a magnitude, different from all the others, including Clojure, Lisp, Haskell, Erlang, whatever, Golang, Python. It's the best language by a magnitude. So I did 5 videos before. Check them out. I go into detail why I think that way, and I demonstrate why it is so. So today I'm going to show typesetting in Mathematica. So first of all, I'm gonna show this sum formula. Okay, sum 1 over n. I'm gonna show you how do you typeset it. So sum 1 over n from 1 to k. Okay, evaluated. Okay, it's a harmonic number. It's a convergent series. Okay, so wait, it's not I forgot the math. Okay, but anyway, so you want to typeset this. So what do? This is all you have to type, and you just select it. Actually, you don't have to select it. You press Control Shift N, I believe. So you go to look at the look at the cell, okay, and convert to Shift Control N, okay, standard form. So let me show you Shift Control N. You see? So you just type that and you press Shift Control N, you get that. Now let's try the full formula. Okay, so let's copy that. Okay, I don't want that. Okay, hold on a second. Delete. So press Control L to copy whatever the previous input. So there are several formats. Let me show you. So this is convenient. So you can choose input form, okay, Shift Control I, which will convert it to the way this is called input form in Mathematica, which is how you type it. So Control Shift I to input form, Control Shift N to standard form. This is what Wolfram language calls standard form. Then there is also a traditional form. Okay, actually let's write it down. Okay. Let's write it down. So Shift Control I, then okay, let me show you. Okay, so Control 7, yeah, undo Alt 7. No, Alt 7 is title. Okay, we are going to start to talk about. Also, I'm going to demonstrate outline mod, so that you have title, subtitle, subheadings, things like that. You can do that. So actually, I'm starting to do it now. Let me see. Alt 7 text form. Okay, yeah. So input form. Let's input form. Press Control Shift I. Okay, so that's the input form. Then Alt 7. Let's see. Alt 7. Then standard form. Press Control Shift N. Okay, so that is the standard form. Then we are going to do traditional form. So let me show you what that is. You select that, and what is the shortcut? Control Shift T. Okay, get rid of the menu. Control Shift T. Control Shift T. So you can see it also renders this in a two-dimensional format. So what's the difference between the standard form and let me paste it here. Control 7. Yeah, okay. Yeah, Alt 7, not Control 7. Yeah, so and so this is the traditional form. So what is the difference between the standard form and the traditional form? They are basically the same. Okay, the difference is that in some traditional, so the standard forms in traditional mathematical notation, there are ambiguities, because mathematical notation is the way it is from evolutionary, is from history. Okay, historical development. It's the mathematical notation you see here. They are not created by someone who designed the whole thing, but rather from historical developments. Like before, we don't have integrals. We don't, we have plus, we have minus. Then when the calculus got invented, there are several competing notations for derivatives, for integrals. For example, here you see a derivative and limit. So there are many competing notations, and gradually, eventually, we converged into one kind of the standard traditional notation. So for example, this is a definite integral, and this is a derivative, the first order derivative of a function f, and here's the limit, and here's the sum, and here's the infinite sum. So those are traditional notations. Now, however, traditional notations sometimes have problems. They are ambiguous. So it's a flaw, and this flaw does not become it only became apparent when you started to use computers to do mathematics, because computers are dumb. Computers are very precise, and it use algorithms to interpret. So when you have a programming language, you need a syntax, you need a grammar. It's very precise. So when you have traditional form of mathematics, sometimes it's ambiguous. Like the computers cannot decide just exactly what you mean. But however, to humans, usually we resolve the meaning by the context. For example, so what's an example of the ambiguity of traditional form? Okay, let me show you a article. Okay, Xali math notation. Just search for that, and you can see an article here. The problems of traditional math notation, and here is kind of a longish article, which I began to document the problems of traditional math notation. And this is a well-known problem, by the way. And this article happened to be, someone posted it to Hacker News a couple of times. So let me give you one example of traditional form. Okay, the ambiguity, the problems of traditional mathematical notation. Okay, for example, the absolute sign. Okay, the absolute negative x. Okay, so for example, the absolute. Okay, so when you have that, okay, so let's say x. Okay, negative x plus let's say plus 3 plus absolute times, okay, let's say times absolute y. Okay, so you have a notation like that. You see, the problem with the absolute symbol is that it's not a bracket notation. So when you have an absolute, kind of a bracket, they do not, there are several ways to interpret this expression. It could mean the absolute value of this x variable, and then the absolute value of the y variable. This is the common interpretation. By context, we understand to mean that. But however, it could also mean, the absolute thing of this expression. Then you take the absolute of the whole thing. Okay, that is kind of a forced interpretation, but it can let's just say this. Okay, z. Okay, so let's modify this. Okay, so this is. So for example, in this notation, how do you interpret that? Suppose y is a variable in a programming language that becomes an operator, that evaluates to an operator. In most languages, you cannot do that, but in Mathematica, you can actually do that. So if y evaluates is a variable that stands for an operator, so then you have this, this is one of the possible expression. Then the interpretation becomes ambiguous, because you can say the absolute value of x then and absolute value of z, or you can say the absolute value of y, then you take the absolute value of the whole thing. So it's ambiguity. So this is just one of the many examples of the flaws and ambiguity of traditional notation. Okay, and I have quite a lot. Let me give you another example, okay, just for the fun of it. X equals to 3, okay? Now, if you are a programmer, it's common to have another expression using double equal. But however, in mathematics, you don't see that. You only see equal sign. So equal sign, let's say y, let's say not 3, okay? So equal sign in traditional math notation has multiple meanings. It can mean an assignment. That is, you assign the variable, you assign the value y to the variable x. Or it can mean equality, a predicate, kind of in logic, it's called predicate. which means, and in programming language, it's also a predicate. Anyway, the predicate in logic and the predicate in programming language, they have entirely different meaning. But anyway, let's forget about logic for now. So the traditional notation of the symbol equal sign can mean assignment, but it can also mean equality. Okay, so when you have this expression, that means x is identical to y. So it's ambiguous, but in math, in math papers, you see a lot of, but you don't use double equal sign. You just use equal sign. But how do you know what does it mean, equality or assignment? You usually know by the context. Human, we read it, we can tell by the context. So these are some of the examples of the problems of the traditional math notation, and there's more. Okay, for example, this is actually a non-trivial problem. This problem actually is non-trivial to the degree it touches upon the fundamental problems of computation and mathematics, the connection, the relationship between math and computation. For example, you might have heard of, if you are a Haskell programmer, Curry-Howard correspondence or Curry-Howard isomorphism. So this is a theory that connects computation with mathematics. Okay, so anyway, we are getting a bit far. So the reason I'm mentioning this is to support my the idea, okay, the claim that the notation, the design of a notation, in fact, is a non-trivial and deep problem that has connections to the foundations of logic and proof theory. Okay, now, in the past 10 years, I have a great interest in proof theory. Proof theory, homotopy type theory, they are all about proofs. How do you do proofs in mathematics? What does it mean? Things like that. And I just want to say, without too much explanation, that the design of mathematical notation is very critical. It's very much tied to the proof theory, the foundation of mathematics and computation. Okay, but let me tell you why. Okay, let me tell you why in a single sentence. The reason the notation is important because in computation, okay, for example, you guys probably heard of lambda calculus, which is the foundation of computation. Lambda calculus is one model of foundation, and there's also combinators. For example, the Hacker News Y Combinator, that they use the name Y Combinator is a specific combinator, which is an expression. And what's a combinator? Combinator is a particular way to model computation. Okay, so, and you also have heard of Turing machine. Okay, Turing machine, combinators, lambda calculus, they are all equivalent models of computation. Okay, sometimes called universal computation, universal computer. So they are equivalent models of computation. So what's the point about them? They are equivalent, but however, they kind of take different approaches. For example, Y Combinator and lambda calculus, they both very much depend on syntax. Essentially, that's what they are. Formally, it's called formal languages. Okay, let me show you some of these articles. Okay, so you can see a Wikipedia about formal languages. Formal language, the study of formal language, is the foundation of theoretical computer science. I would actually claim it's the most fundamental foundation of theoretical computer science. So parsers, compilers, lambda calculus, combinator, they are all based on formal languages, okay? And computability, all those problems, for example, whole team problem, they are all studied by using formal language. And formal language is very interesting, by the way, because it's basically just a symbol. It's just a string replacement. You create rules of string replacement. So this is related to parsers. If you studied parsers in a computer language or regular expression, it's all formal languages about string replacement. In short, in a practical way to explain it, you can just think of it as theories about string replacement. Okay, so that includes lambda calculus and combinator. Okay, so let's look up. Okay, so here we have the Y Combinator, the famous company's startup incubator started by Paul Graham, one of the great Lisp programmer. Okay, combinators. So let's look at Wikipedia. Okay, so you can go read about combinatory logic. That's that. So why is it called logic? Because combinators and lambda calculus, both of them. Why did logicians create them? They are created by logicians. They are created. Lambda calculus and combinators, they are created not to study computer science, okay? They are created to investigate the foundation of mathematics. In other words, proofs and logic. So when can something be true? Can you create a systematic way that automatically find out all possible theorems? If you have that would be wonderful. Because then that means you can create a computer and just let it run. You'll find all possible theorems of the universe. You don't need Einstein. You don't need Newton. You don't need mathematicians anymore, because you just let the machine run and it'll find all possible theorems of the universe. But it turns out it's not the case. So that's why it's lots of study. So let me get back, okay? Combinators, lambda calculus, they were created to study, investigate foundations of mathematics or proof theory, proof systems, and by chance, in turn, they turns out to be fundamental to computer science. Okay, so combinators and lambda calculus, they are both part of. Let me go back. They are both formal languages. Okay. So when we talk about formal languages, it's essentially in a practical sense, it's a string replacement system. Now, that get us back to the notation. So what's a string? If you are a programmer, you know what's a string. You have a string in Perl, Python, C#, C++, in every language, Golang, JavaScript, string. And you can replace string. You can usually do that by regular expressions. Okay, let me show you some regular expressions. Kasali Python rejects. Okay. So I have an article that shows you, this is a tutorial on Python's regular expression, and tutorial regular expression basics, and regular expression flags, and regular expression functions. Okay, so that's a tutorial for Python regular expressions. Find and replace strings. Okay, now let's go back to JavaScript. So I also have an article about articles and tutorials about JavaScript regular expressions. So you can see JavaScript regular expression flags or syntax or functions, or tutorial and tutorial. So a complete tutorial and reference about regular expressions in JavaScript. And I also have a tutorial on Emacs Lisp regular expressions. So you can see there's a tutorial, there's for of regular expression in Emacs. So anyway, so let's go back to where we were. So we were talking about close that, combinatory logic, formal languages, lambda, calculus, Y combinator. So I was saying they are all, in a sense, a string replacement system. Instead of using string, they call them symbols, a sequence of symbols. So you can think of it as a sequence of characters in a string if you are a programmer. So string replacement system. So it has, it's basically, it's deeply tied to computation and foundation of mathematics. So when you do string replacement, so that's why, that's why I say the notation becomes critical, because a sequence of symbols is just a string, and you want to do lambda calculus or combinators of any formal language or parsing, you replace strings, right? So how you design your syntax, what you start with, so that's why it's critical, the notation. Okay, that's kind of a giant digression to formal languages and string, and okay, I think I should write it down, today's topic. So today's talk show, I think let's write it down. Okay, so that's kind of a big digression, so let me write it down. Traditional math notation has many problems. One of them is ambiguity. Okay, the design of notation is critical, and the design of notation or syntax is critical and non-trivial. They are deeply tied to foundation of math, proof theories, and theoretical computation. Okay, that's the second point. Then why is that? Okay, why? For example, formal languages, lambda calculus, combinators, they are all essentially string replacement. And a string is essentially a sequence of symbols, or in terms of industrial programming, it's string. Okay, because when you and for another practical example, parsers. Okay, so what does a parser do? A parser, a programming language parser, it looks at your source code, which is input, then it basically reads every character, and it has to basically transform them into basically another string. Okay, so more or less. Okay, I'm not gonna let me go back to we are getting far. Okay, so let's go back to okay, so let me just say, for another practical example, parsers and regular expressions. Okay, so I'm showing you why do I say they are tied together, and also let me show you let me link to the Curry Harvard correspondence. Okay, So if you don't know what that is, try to read this article. It basically says every mathematical proof has a corresponding program algorithm in in programming. They can they are kind of equivalent. So back to the notation. So I'm trying to tell you why there are the problems of traditional notation, and I gave you two examples: the absolute sign or the norm, and the assignment versus equality. That's ambiguity in traditional math notation. So that's why I'm saying the design of the. So go back one step. I'm trying to explain what's the difference of the standard form and the traditional form in Wolfram language. Okay, now let me explain that. The difference is that in traditional form that basically emulate traditional mathematical notation. But however, when creating the Wolfram language, doing mathematics, because there are many ambiguity problems, therefore Stefan Wolfram created the standard form, which avoids these ambiguities in the traditional notation. For example, let's do integral. Okay, let's do integral. Let's say x squared. Okay, with respect to x. Okay, evaluate that. Okay, we got it wrong. Okay, syntax error. Not integral, integrate. Okay, integrate. Okay, evaluate that. So you integrate x squared, which is the result is x third power over 3 plus a constant. Okay, but let me show you. So let me make this into okay, let's do another. Okay, so here we make it into traditional form. Okay, Control Shift T. So here, this is what you see in traditional calculus, or math textbooks. This is the traditional form. But so what's the problem? There's a problem because you see this D thing. So you have the integral sign, then the expression which is the part you want to integrate. Then comes this dx thing. So what is that D? If you are a programmer, it's a puzzle. Like, where does this D come from? The D here is simply function as kind of a comma or separator. To a mathematician, the D means differential. So it basically, but from a programmer's point of view, the D only functions as a separator of arguments. We are trying to tell the program that x, we want to integrate this expression with respect, to some symbol, and that symbol is x. So the D kind of function as a comma or separator. So from a programming language syntax design point of view, this is not a good notation because you have this mysterious D. So why is it not H? Why is it not A, B, C, D, E, F, G? Why is it D? Well, yeah, because historically, the D to mathematicians, they don't have computers. They just write D. D stand for differential. It reminds them, with respect to X. So that's why in Mathematica, Wolfram language, you have the standard form. Okay, Control Shift N. Okay, it's still D. Okay, yeah. Okay, so anyway, okay, this is not a good example. So, but I can tell you why they still use D. I mean, so the Mathematica typesetting system is created in 1996. Okay, then around 1997 or so, 1995, they were working on this, and then when in 1997 also, Mathematica version 3 came out. Then you have the complete typesetting system. So back then, when this was designed, this D is a big problem. I mean, there's a huge debate between Wolfram, in a Wolfram company, because okay, let me tell you kind of a story. Okay, I may not be accurate. I kind of know. Okay, it's just Stephen Wolfram, he doesn't like this, nor do I. When I see this is a problem. This D is very illogical. It should be banned. So Stephen Wolfram wanted something more like, just comma D or something. But however, that's a problem. You see, the force of convention tradition is very powerful. Just like, for example, computer keyboard, QWERTY layout versus Dvorak layout. Nobody knows what the fuck is Dvorak layout. So the force of convention, for example, let's go to keyboard. Let me kind of ramble in my usual way and tell you about things. For example, in keyboards, most people are familiar with this kind of keyboard. They are comfortable with it. But why is it keyboard this way? Why the keys are kind of slanted? Why the letters are arranged in a weird way? A, D, A, S, D, F. It's all weird. Why? Because history. Because typewriters, mechanical typewriters was that way due to it must, there's many constraints, engineering constraints. Therefore, it becomes that. The staggered layout, so and also the I talked about this many times. The QWERTY, the way the letters are arranged, it's that way not because this is the best design, but rather it's due to historical reasons. So, however, my point here is that tradition, the habit, human habit, tradition, is tremendously powerful. Most people to this day, they have no idea what's a Dvorak. And if you show them a weird keyboard, for example, let me show you some of the weird keyboard. These are designed efficiently. These are well designed. But to average people, your mom or dad, this is weird. This is, they cannot get used to it, even including many programmers today. So the power of convention is a very powerful force, and for good reasons too, because when you have new design, even though technically it's better, but you have to spend time to learn it, and you have basically throw out all history, all the textbooks. If we started to change all traditional math notations, then that means we have to, all the textbooks, millions of them, will be no good anymore, because this is all you have to relearn everything. You have to reteach all the teachers. It's a massive problem. In the same way, just like in United States, we use a imperial measurement system. For example, miles, inches. So why don't we just change them to kilometers, to the metric system the whole world is using? Well, there's a huge cost to pay, because then all the highway signs you have to change to miles, all the cars you have to change to kilometers, and all the people, they are used to miles. Americans, they have to relearn what a kilometer means. Then it's prone to accidents. So the convention and tradition, it has tremendous power, the force and habit, human habit. Therefore, it's not, so therefore, in Wolfram language, they eventually decided to stick with the D. Because if you use something else, let's say a comma or let's not do it here, okay, hold on a second. If you use something else, a comma, or even a paren, something weird, parens doesn't make sense. So maybe you want to use that, anything you do that's different from this form, all the people will find it weird, and basically nobody will use it. So that's a force of convention. So eventually that is why Wolfram language, they gave way to the tradition. So this is the standard form. This is the traditional form. So anyway, back to my explanation. So this is not a good example to illustrate the difference between traditional form and the standard form. But let me show you an example that does illustrate. So for example, absolute value. Okay, norm. Okay, so norm. Let's do a norm of a vector. So norm. So you have a vector 1 and 1. You want to know the length. So in math terminology, that's called the norm. So okay, evaluate it. So the length of a vector x1, y1 is square root of 2. Okay. Now the norm now there's a traditional notation for the norm, which is the double vertical. So let's do that. Control Shift T. Okay. So that's a traditional form for the norm. Okay. But however, we can make it the Wolfram language standard form. Control Shift T. No, not T. Control Shift N. What? Okay, that's not a good example. I should use absolute. Wait. Okay, this is not good. Let's see. Control Shift N for standard form. Okay, I I give up. Wait. So right now I'm trying to show you an example where the traditional form and the standard form differs in a significant way, and right now I'm failing. I failed in giving you an example to show their difference. Okay, let's skip that. Okay, so I can find an example, but that'll take another 5 minutes. So let's check how long have I been talking and check who is watching. Let's see. We need to move on. So I've been talking for 43 minutes. Lots of digression. Okay, so let's continue. Okay, I need to show you the Mathematica notations. So we are so let's just get back to instead of all the digressions, let's go back to the TeX. Oh, where is it? Oh yeah, so there. So let's get back to typing these things in Mathematica. Okay, so let's forget about norm. I'll do that another day. So back to Wolfram language. So we have the input form that's like that. It looks like that. Then we have the standard form looks like that. Then we have the traditional form. Okay. Oh yeah, now I do remember difference between traditional form and standard form. Let's do a derivative. Okay. Let's see if we can do that. What derivative with respect to x? Let's say x squared. So derivative of x squared with respect to x is 2x. Okay, so let's copy that, and now let's show this in traditional form. Okay, yeah, that's the traditional form. Now let's show that in standard form. Control Shift N. There it is. Okay. Yeah. So okay. So this is not okay. So here is an example. So in traditional form, the derivative of x squared is written like that, but in a unambiguous way, in Wolfram language standard form, it's written like that. So you can see the traditional notation for the derivative is ambiguous because you have the fraction, you have the divide. So this can be seen as this, the top expression divided by the second expression, which is completely idiotic. So that's some of the problems of traditional math notation. Okay, and here is an example of the traditional form and the Mathematica standard form, which is very different from the traditional form. Okay, so that's a good example. So now let's go back to how do you type this in Mathematica. So we have shown the sum. So the integral, okay, I think we need to do it fast because I already talked for 40 minutes. So we showed the sum, so let's do an integral. So integral we already showed. So this is how you do the integral. So you just press Control Shift N to get it rendered in standard form, or Control Shift T for the traditional form. So that's an integral. So we've done integral. So what about fraction? So fraction is pretty easy. Okay, so let's just say fraction, x divided by y. Okay, enter. So let's copy that. So let's do this in standard form and in traditional form. Now I'm not going to do standard form anymore. So I mean I'm not going to do the traditional form anymore because most of the time it's identical to the standard form. So anyway, fraction. Okay, so fraction, then you just type x over y / y. So integral. So what about definite integral? So here's the example. So integrate some expression. This can be anything, times f or whatever. Then you want to, so here you say with respect to x, then from a to b, or a and b can be any other expression. Okay, so evaluated that. It actually symbolically, it actually evaluates the whole thing. So let's see. Let's not. Wait, how do you? Hold on a second. So let me see what's the syntax for integrate. Yeah, so. Okay, I think I'm kind of getting too slow, and so let me check the comments. Hello, Luis. Cool, never thought of that. Do you think that is fundamental to give type to the values of the string, or do you prefer a dynamic type system? Okay, that's a programming language design question. We can talk about that for an hour. But it's not related to our topic today. So ask me another day, okay? You are starting to have chauffeur or hair. Greetings, Bart. km and meters, yeah. So anyway, let's get back to the integral, okay? So what is going on here? Okay, so anyway, so let's show that. So this is how you type, this is the syntax for the integration. So Control Shift N. Okay, so you can see that it's typeset. In general, the traditional form is more beautiful. So here is the traditional form. Okay, so integral, so we got definite integral. Then derivative, actually, you can type it like that, okay? Then, for example, copy, then Control Shift N, standard form, Control Shift T, traditional form, okay? Yeah, so here's another example where you can see the difference between traditional form and the Mathematica unambiguous standard form. So why is this ambiguous? Because you can see in the traditional form they are using parentheses. But however, parentheses has multiple purposes in traditional math notation. One, it signifies the grouping, the precedence of expressions. Two, it is used as a bracket for the argument of a function. So it's ambiguous. So how do you know what does this mean exactly? So that's a problem of traditional math notation. So in Wolfram language, they decided, the square bracket is always used for the arguments of a function, while the parenthesis is always used for precedence. Okay, so what about limit? Okay, how do you type limit? Okay, so limit is obvious. Some expression. H goes to x. Okay, let's say a. Okay, so that's how you do limit. So so they actually evaluated this limit and reduced it to just expr symbol. Why? Because when you have a limit and when the variable does not appear in the expression, the result is the expression, something like that. I actually anyway, so let's do that again. So Control-Shift-N for standard form. So here we see, and here Control-Shift-T for traditional form. Wait, did I type this right? Yeah, I got it right. So, but why is the limit not showing correctly? Let's change the expression to 1 over x. No, I don't. Anyway, yeah. So that's how you do limit. Okay, so. So limit. So for example, if you want to, let's do a more complex example of this limit. Okay, so you have this is the traditional meaning of a derivative minus fa divided by h, and h goes to 0. Okay, evaluate. Wait, I don't understand. I mean, this has to do with math. Why is it evaluate to f? Yeah, this is making some assumptions about the function f, because if f is not a well-behaved function, it doesn't become f. But anyway, so here's the expression in standard form and in traditional form. Okay, did we get it right? Oh yeah, wait, we got it wrong. Shit. I got it wrong. Copy, paste. Okay, so traditional form, standard form, traditional form. Okay, that's limit. How do you do square root? Okay, here's a square root. Okay, Control-Shift-N for standard form, Control-Shift-T for traditional form. Okay, now what about matrix? Now here's an example of matrix. Let's make it complex. Square root 2 plus y squared. Okay, copy, paste, paste, and traditional standard form, traditional form. Whenever you see a traditional form, you'll notice here it shows, kind of dot, kind of saw here. Okay, what about matrix? Okay, so let's do a matrix. So in matrix, it's just a nested list in Mathematica. So here we have 1, 2, and 3, 4. So the first row is 1, 2. The second row is 3, 4, and dot 0, 1, 0, 0. Okay, let's see if that evaluates to. Yeah, so it evaluates to 0, 1, and 0, 3. Okay, but how do you format these two? Okay, so let's do copy. Let's do the standard form. It doesn't change. Let's do the traditional form. There it is. Yeah, so in traditional form, the matrix is typically represented by a square bracket, but however, sometimes it's also represented by a parenthesis. Now, I don't know why Mathematica uses parentheses as default. Yeah, because I think the most common way to represent matrix is with square bracket. So anyway, we have matrix. So let's see. Okay, so hold on a second. Let's try to typeset this full expression. Okay, so here you say is equals to that, and okay, that's actually okay. That's not what we want. Nah. Yeah. Anyway, I let's not forget about that. So anyway, so I have showed, how do you type, what's the syntax for these renderings in Mathematica. In fact, you can select the whole notebook and just press Ctrl-Shift-N to transform everything to the mathematical notation. Or you can just select part of it. For example, this squared, this y squared, I can just select that expression and press Ctrl-Shift-N to make that part rendered as a math two-dimensional way. Okay, that's about Mathematica Wolfram language typesetting capabilities. And in fact, you can do this, for example, let's do nested square root, okay? Square root x, let's say nest, okay, let's say nest list. Okay, what's the syntax for nest list? Function expression n, okay? So function square root expression is x. Let's repeat 4 times, okay? Enter. So you get that. Okay, I was trying to show the nested square root, but it actually uses this fraction power, which is equivalent. But I was trying to show the. Anyway, I haven't used Mathematica for a while, so right now I don't know how do you show the nested, the radical symbol. So let's see. Nah, I'm not doing this right. Nah. Yeah, I don't. Okay. This is not what we want. Oh yeah, we forgot that. Oh, there it is. There it is. Let's see. 40, okay? Oh god, this is gonna be humongous. Okay, 40 is too big. Why is it taking so long? Because the rendering, I think it's the rendering is taking so long. 40 nesting, nesting. We are basically nesting the function square root of a number plus that number. It's taking too long. Control period to cancel. Wait. What? How do you cancel evaluation? Alt period. Okay. Alt period to cancel. So let's just say 9. Okay, so we got huge. Yeah, the rendering is the biggest problem. So 9 is too big to see what's the structure. Let's say 3. Okay, so if you just want the last part, you don't want the whatever previous, so you use the nest instead of nest list. Show it. Okay, so let's say 9. Okay, so here you got this huge expression. Wow, even 9 is pretty big. Okay, so that's the, that's the power of Mathematica typesetting capabilities. Okay, now imagine if you are going to do this in TeX or LaTeX. So if you are doing this in TeX, one of the most idiotic thing, all the nerds, the Unix philosophy, the Unix people, Linux people, the tech geekers, they would get excited about TeX and LaTeX, which is the worst design possible. Donald Knuth went the wrong way and created that. That's the worst design possible. So in Mathematica, you can do this, just a few lines, and it's so in math. So one thing that's very different from TeX or LaTeX in Mathematica is that in TeX or LaTeX, all the the syntax, they are not computable expressions. So when you do square root of 2 in LaTeX, I mean, let's just say you want to do 2 squared, okay, 2/3 power. You cannot evaluate it. So 2/3 power is 2 times 2 times 2 is 8. But in TeX, the syntax only allows you to render it. It doesn't allow you to do the actual computation, which is a very bad design. Since you are using a computer, you should be able to have it evaluate. And why do you have to type underscore? How do you do square root here? Do we have a square root? Yes. So this is how you do square root. Backslash sqrt and blah blah blah. You cannot actually evaluate it. But it should be able to, since you are using a computer. So in Mathematica, you don't have the syntax to do the formatting, but instead you simply type the expression. It formats it by itself. It renders it in the two-dimensional notation by itself. So that's the huge difference between the TeX or LaTeX design compared to Mathematica, Wolfram language design for typesetting. Okay, I think I talked enough today for an hour and 6 minutes. So I think that's it for today. I was going to do today. I was going to do talk show. I was going to do talk about the outline features of Mathematica in comparison to OGMod, but I think we'll do that another time. So thank you for watching. Yeah, so if you are wondering, so what is an alternative, a better system for typesetting? Yes, of course, Mathematica, but you have to pay. Student version $300, hobbyist version $300, or a professional version $2,000. But if you want the free, so read my articles. Okay, I give you several alternatives besides Mathematica you can possibly explore. My advice is never ever use TeX, never ever use LaTeX. Stop propagating this crap. Okay, stop being a tech geeker, because this, from the point of view of design, this is the worst possible system for the needs of two-dimensional mathematical expressions, the worst possible system. And why is this system popular? Why is it, this is part of tradition and convention in physics or in mathematics, very common. Why is it very popular? Because one, the most fundamental reason is that it is free. It is free. Everyone wants free stuff, like free pizza. Free, when a computer programming language or a protocol, when it's free, it tends to wipe out everything that's better designed. That's not free. Okay? When a better design system is also free, then the lousy design free one will go away. Like tomorrow, if Mathematica open source, doesn't even need to be open source. If Wolfram language becomes free and without any ties, like you can just use it wherever, without ties to Wolfram research, then the TeX and LaTeX will just disappear overnight. Okay, by the way, Mathematica is free, so you can just go to my website. Okay, so let me show you. So that's it for today. So you can, if you want to just play with Mathematica, it's officially free. You can just go to my website, download Wolfram language for free. There are several ways. One way is buy a Raspberry Pi, $40, or you can download the Wolfram engine or the Wolfram script. Basically, essentially do everything Mathematica, what I've shown today. Actually, I'm not sure they do typesetting. I don't know, but anyway, you can try them. Okay, I haven't studied what's the differences in detail, but anyway, those are free. You can download today, so you can play with. Then I would actually recommend Mathematica. I bought it in 1993 because I wanted to be I wanted to be a great mathematician, and I wanted to have the best tools. Okay, thank you guys. Bye. Okay, so if you like my stuff, donate, buy my Emac list tutorial, or I have quite a few tutorials. Curry Howard correspondence, that's fantastic. So I'm trying to in the next few years, and now I'm trying to study formula. I'm trying to study proof theories much more. So I want to explore that. So again, I have my JavaScript in-depth tutorial, covers everything you need to know JavaScript, and there's also Python tutorial, and they are free on the web too. So but you can buy some of them. Bye guys.